Okay, what's up guys? Yesterday we talked about using Lewis dot structures to represent different molecular compounds. So the examples that we had were H2O or water and CH4 or methane. So one of the things that we need to look at here is in both of these examples we were looking at single bonds. So these bonds here are considered single bonds because each bond only contains 2 electrons. Okay, so we're getting 1 electron from oxygen, 1 electron from hydrogen in order to form a single bond between our oxygen and our hydrogen. Same thing with this bond here. And for our CH4, these bonds are also single bonds because again, hydrogen is contributing one electron, carbon's contributing 1 electron. So we have a total of 2 electrons in this bond. That is a single bond. So each single bond contains 2 electrons. So in addition to the types of bonds that we have in our molecular compounds, I want us to also start noticing the different electron groups. So to figure out the electron groups, what we're going to do is we're going to look at our central atom. In the case of H2O, we're looking at oxygen, and in the case of CH4, we're looking at carbon. The different electron groups that we can have are going to be lone pairs as well as bonding groups. So first looking at H2O, the lone pairs that we have here, we have a lone pair here and a lone pair here. So we have a total of 2 lone pairs. The other electron groups that we're going to look at are our bonding groups. So in this case, our bonding groups will be these 2 single bonds. So we have a total of 2 bonding groups. Since we have 2 lone pairs and 2 bonding groups, we have a total of 4 electron groups. And so it's good to get this practice in now to start being able to identify how many total electron groups we have, how many lone pairs, and how many bonding groups we have. Because this is going to end up determining the shape of our molecular compound or the shape of our molecule. We're going to get more into that when we start talking about VSEPR theory here at the beginning of this next week. So let's do the same thing for CH4. First, I'm going to look at lone pairs. For CH4, number of lone pairs, I have none. And then I'm going to look at my bonding groups. Number of bonding groups, I have 1, 2, 3, 4. So the total number of electron groups is going to be 4. So I have no lone pairs, I have 4 bonding groups, and so I will have 4 total electron groups. So for practice, what I want you to do is draw the Lewis structure of NH3, and then determine the number of lone pairs, the number of bonding groups, and the total number of electron groups. So in these first 2 examples, we're going to move on to different types of bonds. In the first 2 examples with H2O and CH4, we end up seeing single bonds, but with some other compounds like CO2, we don't just share a total of 2 electrons. We end up sharing more than that, and we can have double and triple bonds. So for each bond, a single bond contains 2 shared electrons. For a double bond, we're going to have 4 shared electrons. And for a triple bond, we're going to have 6 shared electrons. So let's look at CO2 and see how it's going to be sharing its electrons, how carbon is going to share its electrons with oxygen in order to form double bonds, and so that all of these elements here, all of these atoms here, end up with a total of 8 valence electrons. So the first thing that we're going to do is we're going to start with carbon as our central atom, and then we'll draw in the valence electrons of carbon. And now we'll add in our oxygens and the valence electrons for our oxygens. So each of our oxygens have a total of 6 valence electrons, and my carbon has a total of 4 valence electrons. So what we're going to see here is that carbon is going to form a double bond with both of these oxygen atoms. So it's going to look something like this. So our first bond will form between those 2 electrons, and then these 2 electrons are going to move and form our second bond. And then we're going to see the same thing happen with our second oxygen and our carbon. So then we can represent each of these bonds with a line. So my first two I'll replace with a line, second two, a second line, and do the same on this other side. So each of these lines represents a single bond. Since I have two going between the same two atoms, this is a double bond. So it has a total of 4 electrons. So in this case, when we're looking at electron groups, we're going to be looking at this central atom, this carbon. So we want to look at the total electron groups that are coming off of this carbon. If we look at our central atom, our carbon, we see that we have no lone pairs on our carbon. But looking at our bonding groups, we're going to count this double bond as just one bonding group because it's going between the same two atoms. So this is one bonding group, and this other double bond is a second bonding group. So we have a total of 2 bonding groups. Since we have 2 bonding groups and no lone pairs, we're going to have a total of 2 electron groups. We talked about yesterday different elements that end up forming diatomic molecules in nature. 2 of those are going to be oxygen and nitrogen, or 2 examples of those are oxygen and nitrogen. So what I want to do is I'm going to have you guys draw the Lewis dot structures of both oxygen and nitrogen, and I want you guys to guess at what type of bond is going to exist between within these molecules. So for this, what I want you to do is, you've already done the practice for NH3. Number NH3 practice as number 1, the practice that we did earlier. For O2, this will be number 2. N2, this will be number 3. So you should have 2 oxygens and 2 nitrogens here. Each of our oxygens have 6 valence electrons. Each of our nitrogens have 5 valence electrons. I like to do it like this, to where my oxygens, my lone electrons here, we've got electron pairs on the back side, and then my lone electrons are facing each other. Same thing with my nitrogens. I've got my electron pair here on the back side, but then these 3 lone electrons are going to be facing each other. It helps us to guess at or predict the type of bond that's going to exist between these 2 atoms. So go ahead, using the Lewis dot structures, I want you to write down your prediction and just tell me whether you think it will be a single bond between them, double bond, triple bond, quadruple bond, whatever type of bond that you think will exist between oxygen, so this is your number 2, and nitrogen is number 3. So on this, you should have the Lewis dot structure, you should have your prediction, Lewis dot structure, your prediction, and then we'll see what happens. So go ahead and make your predictions now, and then we'll go through and see what type of bonds they actually form. Okay, so if you don't have your prediction done yet, pause the video, finish your prediction, and then start playing it again. It doesn't matter, I'm going to give you points regardless of if you get it right or wrong, so don't worry about it. But we're going to first start with oxygen and look at what's going to happen here, what kind of bonds are going to form between a diatomic molecule, O2. So then underneath your prediction, write what sort of bond it actually formed. So for oxygen, it should be a double bond. Let's go ahead and look at nitrogen. So for our nitrogen, our N2, we end up having a triple bond. So again, write this underneath your prediction for the actual bond type. Now, the last thing that I want you guys to tell me for this, so underneath the actual type of bond, I want you to tell me whether this is non-polar or polar. So whether these bonds here will be non-polar or whether they're going to be polar for both oxygen and for nitrogen. So think about it. You've got 2 oxygen atoms bonding together. Will one of these oxygen atoms pull harder on those electrons, are they going to be pulling with the same strength? Same thing with our nitrogen. We've got two nitrogens. Is one of these nitrogens going to be pulling harder on the electrons, making it polar, or are they going to be pulling on those electrons with the same strength, making it nonpolar? So you guys decide whether it's nonpolar or polar, and that will be your last part of the practice. Sorry, one more part of the practice. So once you get the nonpolar and polar done for O2 and N2, I want you to do the same for CO2. So are these double bonds, are these going to be nonpolar or polar for CO2? So think about the electronegativity of carbon versus the electronegativity of oxygen. You should still have that sheet that I gave you that looks like this. So if you don't have it, I'll hold it here for a second. Carbon is 2.5, oxygen is 3.5. So looking at the difference in that electronegativity, tell me whether that bond will be nonpolar or whether that bond will be polar.